Morgan, for the introduction, and thank you to the organizers for inviting me to give this talk. So this is going to be a talk on localized structures in driven dissipative systems, and I'm going to talk about two types of systems, both passive and active systems that are of interest in this particular workshop. So, let me start. So the kinds of structures that I'm interested in are things of this type. So this is a photograph of a ferrofluid with an imposed normal or vertical magnetic field. And the interesting thing that happens in certain parameter regimes is that if you bring a bar magnet towards the surface, you can pull out a peak. And normally what would happen if you remove the bar magnet, the peak would collapse back and the surface would become flat again. But in certain parameter regimes, the peak actually remains after you remove the bar magnet. And so that means that these kinds of structures are created via finite amplitude perturbations. And there is a whole multitude of these. So this is from a picture from Reinhard Richter. This is from some experiments that Reinhard did, where he shows examples of these single peaks and then also bound states of peaks, like these dimers and things of this type, all more or less at the same parameter value. And so I'd like to address the question of why you have so many different structures at nominally identical parameter values and why they have these different structures. Here is another example. This is from an experiment of Hans-Georg Purwins in Münster. You take a low-density gas, you put it between two electrodes, and you apply a potential difference across the electrodes. And when the potential difference is large enough, you get an electrical discharge, electrical breakdown. And so you get current flowing through the medium from one electrode to the other. And of course, this is like lightning in the lab, and so you see light emitted from these discharges, and so you can image it very nicely. And so this is what was done in the experiments. And you get different kinds of structures. You get these kind of hexagonal crystalline states. You get states which are analogous perhaps to a liquid, where these filaments move around randomly. You can get dilute structures like this, perhaps gas-like. You can get change of these filaments. And then you get situations like this, where, for example, you have a solid, in other words, stationary structure with some filaments moving around randomly. It's more like a coexistence, say, between a gas and a solid or something like this. There are other examples of localized structures. So I've been interested in buckling. So this is an example of where you take a cylinder and you axially load it. And when the load exceeds a particular threshold, the cylinder starts to buckle. So this is a stationary buckled state of a cylinder. And you see that the buckling takes place along the central periphery of the cylinder. You can visualize this or represent this behavior in a bifurcation diagram. So on the vertical axis here is the loading of the cylinder. Sorry.
What were the colors on the previous one?
The colors just represent the displacement. Sorry, so on the vertical axis is the load that's applied. And so here is the threshold for the buckling instability. You notice that when the cylinder is unbuckled, it's actually much stronger than when it's partially buckled. So these are all steady states, but partially buckled states. And you can see that here, the cylinder can support much less weight. And then at some point, you can load it up again. But if you load it too much, it snaps through to a new state, new buckled state. You can load it up some more and snaps through again. And so there's a whole sequence of these stable buckled states that you can see in this region. And they correspond to the structure that you saw in the previous slide, a structure with 4 rows of these cells, 6 rows of the cells, and so on. And if you have an infinite cylinder, you're going to have more and more of these possible steady buckled states of the system. And they're all organized along this line here, which I'm going to refer to as the Maxwell load, for reasons that will become apparent very shortly. So these examples that I've mentioned, and there are many more, they have completely different physics, right? But you still would like to understand, what do these structures have in common? And for that purpose, a useful way of proceeding is to construct a mathematical model that behaves like these systems. So this model is not supposed to capture the physics, but it's supposed to capture the behavior of these disparate systems. And the equation I'm going to talk about is the famous Swift-Homburg equation written here. The important thing is that it's an equation for a scalar quantity u, first order in time. There is a parameter r, which is going to be a bifurcation-like parameter that I'm going to vary. The equation has a characteristic scale given by 2 pi over kc, so there is some intrinsic wavelength. And then there are some nonlinear terms, and the nonlinear terms are very important here. You have a choice, of course, in this kind of modeling, what nonlinear terms you will choose. But the important thing is to pick a bistable nonlinearity so that, for example, the u squared term here is destabilizing and the u cubed is stabilizing. And then you can do the same kind of experiment that was done in Richter's lab that I showed at the beginning. You can generate a localized perturbation somewhere in the plane. You allow it to relax. And if you're in the right parameter regime, maybe it will not collapse back to the flat state, the homogeneous state, but it will remain as a persistent localized structure like this target pattern here. Or you can have, generate a new perturbation over here, and that might relax to a spot. A different perturbation might relax to a hexagonal structure, things of that type. Yes?
Maybe too early to ask this. One other important feature of Swift-Homburg is that it's potential.
Oh, absolutely.
At least for the discharge problem, that might be
absolutely, yes. Absolutely, I'm coming to that, in fact. And of course, depending on what competing, or maybe I should say antagonistic nonlinearities you choose, because that's a word that's been used a lot here, you might get different kinds of structures. But still, the system generates the localized states, and it generates the localized states in the region of bistability between an extended pattern state and the homogeneous state. And I'll come to describe that in just a moment. So to understand the behavior of this equation, let's just look at it first in 1D. So I've written the same equation here in 1D. The important properties of the equations are that it's fourth order in space. This is essential for what I'm going to talk about. That there is this intrinsic length scale that I've already mentioned, that you have bistability due to these competing nonlinearities. And finally, what is very useful for analysis is that it's reversible in space. So in this particular case, that's a very simple symmetry, just x goes to minus x. And as was mentioned just a moment ago, the equation is actually very nice because it's a gradient system, and there is a free energy given by this expression. And so essentially what I'm going to be talking about in trying to understand stable localized structure is the energy landscape of this free energy. And of course, each stable localized state was going to correspond to a local minimum of this free energy. And it turns out that this free energy has a very complicated energy landscape. So how do we analyze these kinds of problems? Well, the simplest thing, of course, is to look at the linear problem first. And so here I've linearized the equation. That was very easy. I just dropped the nonlinear term. And there are two ways which people generally think about these kinds of linear problems. One is in the time domain. They look for solutions that grow with some growth rate sigma. And so that's written here. And you see, of course, when the real part of sigma, in this case, sigma is real. So when sigma is real, the perturbation of u equals 0 is going to grow in time. When sigma is negative, it's going to decay. And that neutral stability curve is drawn over here. So this is the parameter r, the bifurcation parameter on the vertical axis, and the wave number of the disturbance is on the horizontal axis. And of course, if you increase the bifurcation parameter, then at this particular value, r critical, which is equal to 0 here, this is where you first generate an instability. This is the standard way of thinking about a pattern formation. But I actually prefer it a slightly different way. I want to just look at stationary or time-independent solutions. And so I would like to look at solutions that just grow like e to the lambda x, where lambda is a spatial growth. And so for r greater than 0, lambda is just plus or minus iq. And there are two possible wave numbers, Q minus and Q plus, and these just correspond to spatially periodic structures. So that's the spatially extended state that I'm going to be interested in. And then as you decrease R, these two wave numbers come together and they actually coalesce at this red dot. That's the onset of the instability. And so there is a new way, therefore, to think about this red dot, and that is that it's a collision of these spatial eigenvalues, right? It's what we call a reversible Hopf bifurcation, Hopf because these are complex eigenvalues in space with 1-1 resonance, because the two wave numbers that come together at the red dot are the same. Okay. And you can analyze, this kind of instability, but the important thing I want to emphasize for now is that when R is greater than 0, you have these two imaginary eigenvalues, IQ plus, IQ minus, the complex conjugates. When R is 0, these two collide on the imaginary axis, and then when R is less than 0, they split and move off into the complex plane. So that's a typical behavior of reversible systems. In fact, this is in fact a Hamiltonian system in space. And so this splitting is the generic Hopf bifurcation of a Hamiltonian system. And the important thing here is that I have two eigenvalues which have positive growth rate and two eigenvalues which have negative growth rate. And so the task to identify localized structures is this. You've identified a growth from 0. You've identified decay back to 0. You want to somehow connect these together, right? And for that, you need nonlinearity. That's the basic idea. And so if you analyze this bifurcation, it's a 1-1 Hopf bifurcation in space, you find that the bifurcation generates two types of structures simultaneously. It generates these spatially extended patterns, and then it also generates localized structures, where you have an envelope, sectional-like envelope, and then the oscillations inside the envelope. Okay. And it turns out that these localized structures come in families, given by a discrete set of values of this translation phase, phi. And in the case of the 2-3 Swift-Homburg, the quadratic cubic one, there are just two values of phi that are permitted. And so what that means is that if you look at a bifurcation diagram showing the norm of the solution as a function of the bifurcation parameter, I've just analyzed this region over here. The homogeneous state is stable until you reach R equals 0. You have a bifurcation to a periodic state. That's the extended state. In red here, it starts unstable because, this happens all in the subcritical regime, R less than 0, where you have the positive real part and negative real part spatial eigenvalues. So you're in the subcritical regime. And at the same time, you generate a pair of localized solutions, which I'm calling L0, L pi, also unstable. But when they enter this shaded region here, they start to oscillate back and forth in behavior that we refer to as snaking behavior. And the distinction between these solutions is that the L0 solutions have a peak in the middle, and the L pi solutions have a dip in the middle. And the solid line here indicates stable solutions, and so you can see that you have a very large multiplicity of coexisting stable solutions, and which one you will see will depend on the finite amplitude perturbation that you impose on the system. So this is a more detailed picture of that. So you have these two snaking branches intertwined, and they are connected via these links, which we call ladders. And these correspond to non-symmetric solutions, for example, a solution like this. And because this is a gradient system, these non-symmetric solutions are actually stationary solutions of the system. Later on, when I talk about active systems, these solutions will in fact move. So how do we understand the origin of this multiplicity of different states? Well, the way I like to think about it is in terms of analogy with phase transitions. If I have coexistence, say, of two uniform states, like, say, a liquid phase and a gas phase, then I can have coexistence between those states, of course, at the critical temperature. If I change the critical temperature, for example, I increase it, then of course the liquid drop is going to evaporate, so this front is going to move inwards. Conversely, if I decrease the temperature, the vapor is going to condense and the drop is going to grow, and so this interface that I've inserted here at no cost is going to move outwards. So to have stationary solutions of this type, I must be at a particular temperature, right, the critical temperature. Now, our problem is a little bit like this, but the difference is that we have competition between a homogeneous and a crystalline state, like this periodic structure that you see here, and is bounded by fronts at either end that connect it to the homogeneous flat state. And because of the heterogeneity here, there is a new physics that comes into this picture that's referred to generally as pinning, because this front here is pinned to the oscillations behind it. And so there's a pinning potential, and you have to overcome the pinning potential before the front can move, and that means that you can change the temperature away from the critical by some amount and still generate stationary solutions. You have to increase the temperature or decrease the temperature by a finite amount before the fronts depin and start to move. In that region, through this pinning effect, you can get a multitude of other states, which I'm not going to talk about. You can get these bound states that you saw earlier, and many other things. So this so-called pinning region or snaking region contains a huge number of different states. Many of them are stable, and each of those stable states, of course, corresponds to a local minimum of that free energy that I wrote down earlier. You can compute the pinning region. It starts exponentially thin here at this bifurcation point, and then it spreads out. And notice that it straddles the Maxwell point. So what is the Maxwell point? The Maxwell point corresponds exactly to the balance or between the free energy of the periodic structure and the free energy of the homogeneous state. And you can see that the pinning or snaking region is basically generated by a broadening of this Maxwell line or Maxwell point. And that broadening is a consequence of this pinning effect that I've just mentioned, and it is that is responsible for generating the multitude of these different localized states, all of which coexist in this blue region. And if you go outside of the pinning region, of course, then you don't have stationary solutions anymore, and so structures evolve in time. So here is time evolving upwards, and you can see if you go to the situation where the lower energy state is the crystalline state, the periodic state, that you generate periodically, or you nucleate new wavelengths. And this is the way that the system is approaching the lower energy state, the crystalline state. And you can develop some theory for the nucleation time. This is the solid line here, and it agrees well with the measurements. And of course, if you go to the other side of the pinning region, then the lowest energy state is the homogeneous state. And then what happens is that you sequentially delete wavelengths as the state collapses to the lowest energy state. Now in 2D, of course, it's more interesting. You have many more possibilities. So here is a partial phase diagram for the 2-3 Zwift-Homburg equation, the quadratic cubic one. And you see, hexagonal localized hexagons, stable spots, targets. I've already shown you some pictures of these. I just want to spend a minute telling you about how these structures evolve as you follow a branch of steady solutions. For example, here for hexagons. So if I'm here at location 1, you see a nice hexagonal patch. If I follow the branch numerically by incrementing this parameter r, then I will eventually end up at location 2, and you see that you've added cells in the middle of each facet of this hexagonal patch. If you follow it a bit further, you add new cells either side, and you have to go to location 4 before you get another regular hexagonal patch. And so this is the way that these structures grow as you vary parameters. They're all steady solutions. You can do this for these hexagonal stripe-like structures where you have snaking within snaking, if I can use that expression. You can see that this snake here in purple or whatever color that is corresponds to adding cells along the side, and then these big oscillations correspond to adding whole rows of these cells. So there's a very regular kind of prescribed mechanism whereby these structures grow as you vary parameters. And of course, there are more possibilities in 2D. So this is for 3-5, the cubic quintic. Smith-Homburg equation, you get these kinds of barrel-like structures that behave in a similar fashion. I don't want to say any more about this. You can get these, I don't know what to call these, but anyway. So there are a lot of different localized structures that can be generated in 2 dimensions, and they all grow in this kind of a fashion through this snaking process, which corresponds to the addition of new internal structure. So let me now move on to...
just one question.
Yes, please.
So, given that there's a free energy, if you add a bit of noise to that problem, presumably it will actually just finally select the lowest free energy and all this other stuff just goes. Is that right?
I certainly believe that. We have not actually looked at the stochastic version of these problems, but I absolutely expect that eventually, you know, it's a Kramers problem. You have to go over the...
But the point is, you're saying even where you would normally think the boring state is the stable, thermodynamically favored solution, you have all these other...
You have all these other states, and in fact, we believe that you know, some of these localized solutions can serve as, you know, as nuclei, in fact, for you know that nucleate, say, the process of crystallization,
Right.
because they are long-lived states and so on. But yes.
So how would I then think about this as a nucleation probe? So my naive picture of crystal nucleation would be there is a nucleus of the solid state that just keeps growing. So would that mean that in fact crystallization is a series of nucleation events where in every nucleation event I add a new key?
Can I come to that in just a moment? Because I'm getting to that. So I want to now say a few words about you know, how you might use some of these ideas in the context of crystallization. And so let me just review a few things just in one slide about the density functional theory. So this is a theory for the free energy of a system of particles. There is the free gas. This is just rho log rho, the usually entropic contribution. And there is a contribution from two-body interactions mediated via this potential V. And of course, what you want to do is you want to find minima of this free energy subject to some constraints. That could be from a confining potential called phi here, and of course mass conservation through this Lagrange multiplier mu. And the minima then correspond to solutions of this integral equation that depend on the confining potential and this chemical potential mu. And you're interested in solutions of this equation, for example, when phi is 0, that have solutions where rho is either constant, so you can think of that as a liquid phase, or where it's crystalline, and that would correspond to rho being a periodic function of x. Now you can look at near equilibrium behavior by including time dependence in this kind of description, and that leads to so-called dynamical density functional theory, described by this equation where gamma is the mobility. And this works actually very well for many extended systems, including modeling Brownian particle simulations and things of that type. But I want to take this equation, I actually want to simplify that just a little bit more by writing an equation for an order parameter phi, which just measures the departure of the density away from the uniform background. So again, phi equals a constant is going to be the homogeneous state, the liquid state, and phi periodic state in space is going to correspond to a crystalline state. And when you do that, essentially through a gradient, the usual kind of gradient expansion, you end up with this equation here, which people usually call the phase field crystal equation. alpha is the mobility here. F has this Swift-Homburg form. This is like 5-4 theory, except you have this internal length scale given by the wave number QC. And then the dynamics follows this equation, which is the equation that we've had, except for the Laplacian in front, right? So that's, it's natural to call this the conserved Swift-Homburg equation. And if you're interested in steady states, and I've been talking about mostly steady states, then the steady states solve this equation where mu again is the chemical potential. And so this is an elliptic, nonlinear elliptic equation. And the kind of question that's of interest is, what are the possible solutions of this? And if you look at this in 1D, so this is the 1D version, so this is now just an ODE, you can look at the solutions in terms of, the grand potential or its density, little omega here, and you can also look at it in terms of the free energy density, little f here, or in terms of the amplitude or norm of the solution defined here. So I'm going to show just a few pictures of what some of the solutions look like. We've seen these pictures before. So here R, that's the bifurcation parameter, that really corresponds to temperature. And as you decrease R, you make it more and more negative. You're cooling the system down. And when you cross this blue curve, the liquid phase becomes linearly unstable to the onset of periodic structures, in other words, crystallization. And then in between these two curves, so these are the coexistence curves between the liquid phase and the crystalline phase. So these tie lines just represent solutions which are in thermodynamic equilibrium with the same chemical potential and the same pressure. So that's the usual picture that you get. If you look at the solutions, then you see, here is the analog of the bifurcation diagram that I've been talking about. Here is the conserved phi, so that's the mass, if you like, in the system, and this is the response of the system on the vertical axis. The liquid phase is stable up to here, and then here is the crystalline state. It's now supercritical, actually, but if the domain is large, almost immediately becomes unstable to these localized states, and you again have this pair of oscillating branches like we had before. The important thing for our purposes is that these oscillating branches, which coexist with the stable liquid phase here, actually have a lower energy than the liquid phase. So here is the energy of the liquid phase. Here is the energy of the crystalline phase. You notice that the energy of these localized states is actually the global minimum here. And if you replot this, for example, you plot the chemical potential as a function of the mass, you get this behavior that we've already seen. It's just turned by 90 degrees. And you can also plot the grand canonical potential density. And so this is a kind of summary of what you get. Remember, R is a temperature-like parameter. If I decrease R, make it more and more negative, you start developing these branches of localized states. As the temperature gets lower and lower, the region where you get localized states increases in terms of the chemical potential, and you create more and more of these metastable or maybe globally stable localized structures. Now in 3D, we don't have a full phase diagram, but here is an attempt at generating one again. So this is the temperature parameter, this is the mass, and you can see now coexistence between the liquid phase called uniform here, bumps, so that's like a hexatic phase, a stripe-like phase, and then you have hexatic holes, if you like, over here. I'm just going to show you what happens as you go in, at this temperature, if you go from this region to here, towards the liquid phase. You see that, as you would expect, initially you start essentially with stripes, but then as you go into the bump region, you get more and more of these hexagonal structures appearing, and then eventually the structure falls apart when you're close to the binodal between the hexagonal structures and the liquid phase. And this just shows kind of a more detail of how these structures fall apart as you approach that binodal line. And of course, you can have three-dimensional structures, and these are, complicated things to visualize, I guess, but this shows similar behavior going from, laminal structures to different types of three-dimensional, FCC, BCC kind of structures, and eventually the structure falls apart as you enter the liquid phase. So let's talk about what I'm calling here thermodynamic stability. So what we're plotting here is the bifurcation diagrams that you've already seen. So here is the mass in the system. Here is the chemical potential on the vertical axis. And I'm indicating here in solid line the global minima of the free energy as if, for different values of phi naught. And so here the global minimum is the liquid phase, and then the local minimum is a crystalline state. It's a localized nucleus, if you like. At different sizes, are the global minima as you go along here. And then finally, the global minimum is the spatially extended crystal here on the far right. And you can see again the free energy showing that you have minima for the localized structures. And then if you increase the domain, in other words, you're trying to take the thermodynamic limit, then you see that these zigzags that you saw in the previous slide, they converge onto the Maxwell line. But they converge in this pointwise way, through these zigzags basically collapsing onto the Maxwell line. So this is perhaps an answer to Mikhail's question. These things do play a role, and you should really think of the Maxwell line as consisting of lots of transitions between structures or nuclei of different sizes. You can do this for these quasi-1D structures, like here, we've seen these before, and the picture is similar. For a smaller domain, you have global minima, which look like this, and then if you increase the domain, again, you're collapsing towards the Maxwell line. And if you do this for these hexagonal structures, you get similar sort of behavior that I'm illustrating here. It's a little more complicated, but again, in this Maxwell region, you have global minima of different sizes of these hexagonal patches. And again, it appears, although we haven't fully established that these things will eventually converge to the Maxwell line. Of course, this here, is more complicated because you have more interfaces, so there's more contribution to the free energy. And so the convergence rate is slower. And if you summarize these results, you see that these 1D structures have jumps in the chemical potential as a function of the domain size. They go, as a parallel here with the exponent -1 for these quasi one-dimensional states. You have a different exponent for the hexagonal patches, as shown here, and we don't understand the value of this at all. And maybe Uwe understands it. But let me just mention, you can play this sort of game in 2D and 3D with more complicated equations. And so what I've done here is I've just changed the linear problem here in such a way that the growth rate of the linear instability has two peaks, one at wave number 1, the other at wave number q. And they have growth rates, which I'm calling R1 and RQ. And if you look here in the subcritical regime, in other words, where RQ and R1 are both negative, right, that's the subcritical regime, you can generate a stable quasicrystalline structure like this 12-fold quasicrystal over here. And you can do this in 3D, and you can generate, for example, these icosahedral quasicrystals in 3D. This is a slice through a particular facet of that. And then you can also find localized structures, so these are kind of like localized quasicrystals with any superposed envelope. And these behave in somewhat similar fashion to what I've been talking about with this kind of snaking behavior.
So there's one small
Yes.
question about quasicrystals.
Yes.
If you took just the Swift-Kronberg functional as it is, Mermin and Tryon many years ago, 40 years ago, so found quasicrystalline minimum for that on its own. The idea being not that you need two competing lengths, but if you have wave vectors at, say, in 2 dimensions 72 degrees to each other, then the sum of those 2 wave vectors points is incommensurate with these guys. So you can get competing, incommensurate competing lengths purely by choosing, condensing onto the same shell of wave vectors and not having 2. You never see that?
We have not seen that, but I know about this construction. The idea here is essentially that we have 2 circles of spheres of unstable wave numbers, and the idea is that the wave numbers on one sphere generate wave numbers on the other, and vice versa.
Right.
So you have this mutual.
They talk to each other.
Yeah, they talk to each other, and this is.
I was just saying, basically, we have a geometrically ordained incommensurateness instead by just choosing wave vector as a fixed length for a different angle.
No, I completely agree with that. But this is actually a pretty common mechanism for generating quasi-crystalline structures. For example, in Faraday waves, vertically vibrated fluid layers and things like this. Is usually through these 2 competing states, wave numbers. So let me finally move to the active part of the talk. So I'm going to just talk about one particular model from Hartmut Löwen. There are, of course, many competing models that people have looked at, and we have looked at also. But I just want to say a few words about this particular model, which is a conserved equation for phi, but it's coupled to a polarization field P, which itself has a conserved part, but a non-conserved part, right? And they are coupled through this parameter V0, which I'm going to call the activity parameter. So there is some diffusion coefficient dr, which is assumed to be positive here. So the free energy of the system is going to be taken to be, the phase field crystal, the conserved Swift-Holmberg kind of free energy, and there's going to be a corresponding part from the polarization field. I've written those down here. So in this kind of a model, you can get spontaneous polarization if this coefficient C2 is non-zero. So in order to just avoid that and look at the effect of the coupling to the polarization field, I'm mostly going to put the C2 coefficient equal to 0. So when you do that, you generate the following equations. So here they are. So this bit we've already seen. This is the conserved Swift-Holmberg equation. Here again, I'm using this parameter R for a temperature-like parameter. The difference is that I've taken out the mean of phi here, phi bar, so that the integral of phi over the domain is now actually 0, okay? And it's coupled to the polarization over here, and here is the polarization equation. This one is actually a linear equation in this particular case. So the thing that I want to mention about this is that equations or models like this may have some special properties. And a particular important property of this model is that there is a symmetry. I'm calling it kappa here, where if you reflect x and you change the sign of the polarization, the equations are unchanged. And so that's an important symmetry. And the statement that I want to make is that if you have kappa symmetric solutions, in other words, these could be extended or localized solutions with this symmetry, then those solutions have to be stationary. But it turns out that for a model like this, the converse is not true. In other words, that solutions that break the kappa symmetry have to move. That does not hold for this equation. And that is a surprise, because this equation actually behaves in a non-generic way. So let's try to understand that a little bit. So if I look for traveling solutions that travel with speed c, so of course the obvious thing to do is you go into the moving frame, and then you're looking for stationary solutions of the equations in the moving frame. And so I've written them here, okay? Now, if kappa is a symmetric solution, right, it satisfies those symmetry properties on the previous line, then for example, the divergence of P here, that is unchanged. Why? Because P changes sign and X changes sign, okay? So this is unchanged. This is unchanged because phi doesn't change sign, and these are all quadratic things. So the only term that changes sign is this one, because phi doesn't change sign, and the gradient changes sign, okay? So, and so you get, you know, if you apply the symmetry kappa, phi and P do not change because they are symmetric, but the equation changes, right? And so you conclude immediately that if you have a symmetric state, it cannot move, right? It cannot move, it has to be at rest. Now the important thing is that, you know, the converse of this does not hold, and you can get asymmetric solutions, in other words, solutions that break this kappa symmetry, that are in fact at rest. So let's talk about some solutions of this model, just as an example. So here I've taken the activity parameter to be 0. Yeah. So this is just the, you know, the phase field crystal model, right? This conserved straightforward equation, and this is just a recap of what we've already learned. The liquid phase is stable up to here. This is the crystalline structure appearing here. That's the state labeled 4 here. And then here are the various localized solutions that we've been talking about, okay? So that's not a surprise at this point, I hope. But now I've increased the activity parameter to this value, which is above a threshold for the onset of motion. And then you get a very similar picture, but now all of these states are traveling. So, for example, the crystalline state is traveling, and then these localized structures travel. And you notice also the growth behavior as you follow the branch, you know, past these folds, that also changes because there is now a preferred direction of motion. And this picture down here shows actually, you know, the speed of these different solutions you know, as a function of the parameter r. Now here is a phase diagram for this active case. So what you see here is the mass on the vertical axis. It's called psi bar, unfortunately, here, as a function of the activity parameter V naught. So here is the liquid phase down here. Now to the left of this vertical white line, you have stationary solutions. In other words, solutions that essentially behave like the passive case. So we've seen examples of that. So here are the localized states. Here are, you know, are the stationary, for example, hexagonal structures over here. As you cross this line, and we can predict exactly where that line is, you find that the structures start to travel. So, for example, here is, you know, what the solution looks like at this location. So this shows the solution, this location, and so on and so forth. So there is a transition to these traveling states at a critical activity level. And what you find if you solve equations, the sign of V naught doesn't matter, but you find something very unexpected. So here is the crystalline state over here. Here are these localized solutions. So let's look at this one. So here is a bifurcation. That's like that link state that we talked about. This link state generically should travel because it consists of solutions which are asymmetric with respect to that reflection symmetry kappa. An example would be this state. This state should be traveling, but here it's actually a stationary state, and then it undergoes a drift bifurcation, but it's not a drift pitchfork, it's a drift transcritical bifurcation, which again is unexpected behavior, okay? And then you create a drifting solution here in black, so that an example would be D, you know, that solution is now still asymmetric, of course, and it's drifting, but it's created in this non-generic fashion. So just a couple of words about that before I finish. So we can think in terms of a system of fields, some of which are non-conserved, called N, some of which are conserved, called C here, obeying, you know, the usual kinds of dynamics here, gradient dynamics, conserved gradient dynamics. We can write this, it's convenient to do that as a single equation here by defining this operator dxx so that it's a second derivative if you have a conserved solution, a conserved field, and it's just -1 if it's non-conserved. So that's just notation. And then the important thing is this, that if all these coefficients alpha I that appear in those equations are of the same sign, then the system is, a proper gradient system, conserved system, with a certain Lyapunov function here. The important thing about these mobilities, or these quantities alpha I being all of the same sign, is that the free energy is bounded from below, so you have a global minimum. If some are positive, some are negative, then it's a problem. It looks like you have a gradient system, but it's a bottomless gradient system, because there are some directions along which you give up energy, but there are other directions along which you can gain energy. And that, of course, is something that you need in order to get persistent time dependence. So we've called this spurious gradient dynamics, because, in fact, f is not a Lyapunov function anymore. And so if you take this model that I talked about, this, the coupled phi conserved dynamics to the polarization, you can write it in this form, but it's essentially explicit form of what I've just described, but the important thing is that you have an alpha 1 which is positive, alpha 2 which is negative, right? And so that's an example of one of these systems, and it is in fact, what happens, this is what's responsible for the fact that you can have asymmetric structures which are stationary and not moving. And the way to fix that is to add this term. And then the system behaves generically. So it's just perhaps a word of warning that, one should be careful about studying models which are not too special because they may exhibit non-generic behavior. So this is my last slide. So I've told you a little bit about localized structures in 1D, 2D, 3D, described by systems which I believe are relevant to the topic of this workshop, both in passive and active systems. We've seen, how they play an important role in the crystallization transition from a liquid, and then also I pointed out that some active matter models possess this non-generic behavior, which I think should be avoided in constructing models. So, thank you.
Thanks, Edgar, for the wonderful talk. We have time for questions. Sorry. I have one concerning these localized structures. It sounded to me that you have this collision of eigenvalues, and then you have these localized structures. That's a story other people tell in the context of topological phase transitions. So if you were to look at the eigenvectors, is this a topology, the eigenvectors?
Okay, so I would have to think about that. I would be surprised, but because you have two unstable directions, two stable directions in this example. The eigenvectors are complex conjugates of one another. But I haven't. I don't know. I'm sorry. Yeah.
And with the crystallization transition, I see that you have all these states appearing. But if I actually looked at something undergoing nucleation, what would you see?
Well, so to really to model that, I think you would have to include you would have to do it at finite temperature. And so you would get, thermally activated nuclei. And of course, there are different types of nuclei in 2D or 3D. And one of the ideas that we have, which we haven't really explored, is that if the preferred nuclei have a certain kind of structure, they may frustrate the generation of the full crystal, right? that is actually thermodynamically preferred as an extended, crystalline structure. So then these nuclei, if they, are somehow incommensurate with the crystalline structure, may actually have an important effect on the crystallization process. But the naive picture is you just have a front propagating, the crystal propagates into the liquid, then the question is, what kind of a front is this? Is it a pulled front, meaning that its speed is described by, essentially linear theory, the marginal stability criterion, because the liquid phase is unstable. But there are situations where the crystal can propagate, as a pushed front, meaning that the speed is actually generated non-linearly, or determined non-linearly, even though you're invading, an unstable liquid state. So there are different situations that can arise.
You're over time already, so let's thank Edgar again.